Hello, I'm Professor Afshar at Glendale Community College. This is Physics 103, Lecture 53. In this lecture, we'll discuss microstates versus macrostates and entropy. These topics are covered in Chapter 22 of our textbook by Servoy and Jouet. Understanding the concept of entropy requires a fair amount of background information. So let's start with a review of the second law of thermodynamics, which we discussed in our last lecture. Recall that there are three forms or versions of the second law of thermodynamics. They're all essentially saying the same thing, but they're saying it in different contexts and for different applications. The Kelvin-Planck version of the second law states that for any heat engine, W must be less than QH. Recall that W is the output of work from the heat engine and QH is the input of heat or thermal energy into the heat engine. Here everything is in absolute value signs, so we're talking about the magnitudes of these quantities. This inequality has some consequences. One of them is that QC cannot equal to 0. QC is the output of thermal energy from the working substance into the cold reservoir. We refer to QC as the exhaust of the heat engine. So this inequality can be interpreted to mean that some energy is always wasted as exhaust. If we could somehow be clever enough to design a heat engine where QC is equal to 0, then we would have an engine that has no waste, has no exhaust. However, the second law of thermodynamics tells us that that is not possible. The Clausius version tells us that for any heat pump, QC is less than QH. Remember that a heat pump essentially transfers thermal energy upstream. It transfers thermal energy from the cold reservoir to the hot reservoir. This inequality has some consequences. One of them is that W cannot be equal to 0. W is the input of work into the heat pump, and so we interpret this inequality to mean that heat does not spontaneously flow from cold to hot objects. Heat does not by itself flow from cold to hot. It does so only when there is some input of work. Now, in our last lecture, I also explained that the second law is not really about impossibility. It's rather about extreme improbability. So when I say heat does not spontaneously flow from cold to hot objects, what I'm really saying is that heat can flow from cold to hot objects spontaneously. However, that would be very, very, very unlikely. A little more precisely, given two realistic systems, one cold and the other hot, the probability that heat will by itself, without any input of work or interference from a third system, the probability that energy would flow from the cold object into the hot object is so low that we may as well consider it to be impossible. Of course, I am talking about realistic systems. In other words, I'm thinking of systems that have, let's say, more than 1,000 atoms. If the system on the right had 2 atoms and the system on the left had 2 atoms, then yes, it would be possible, maybe even probable, for thermal energy to spontaneously go from cold to hot. However, for realistic systems, a system that might be of some practical utility to human beings, this would not happen. Note that a single grain of sand has more than 10 to the 18 atoms in it. So any kind of a realistic system that would have some practical engineering applications would certainly have more than 1,000 atoms in it, and for such systems, the probability of spontaneous flow from cold to hot is extremely unlikely. Of course, to make all of this more precise, we need to be able to measure probability. So we're going to spend the next few slides talking about how probability is measured for a system of individual atoms. So the probability of a system doing something depends on the state of the system. And by the state of the system, I mean a precise description of the important properties or characteristics of that system. For example, consider an ideal gas confined to some volume. More precisely, let's say we have n atoms or molecules of an ideal gas confined to a volume, let's say confined to a box. At a given time, each one of these atoms occupies a certain position inside that box, so we can start our description of the system by specifying the coordinates of these molecules or atoms. We can start by measuring and recording the x, y, and z coordinates for atom number 1, and then we can measure and record the x, y, z coordinates for atom number 2, and so on until we get to the nth atom. Now, presumably, these atoms are also moving inside the box, so we would also like to know the velocities of these atoms. That way, if we look at the velocities of any two particles and notice that they're moving towards each other on a collision course, then we can use something like conservation of momentum to figure out what happens to them after the collision. This type of a detailed description of the properties of the system is referred to as a microstate because it's a very microscopic description of the state of the system. A microstate, from a theoretical point of view, is a very desirable description of what the system is doing. We can use its microstate to calculate the probability of a system doing something. Unfortunately, this is not a very practical description for realistic systems. A realistic system might consist of, let's say, 1 mole of atoms. Recall that a mole is approximately 6 times 10 to the 23 particles. Measuring and writing down or even recording on a computer the positions and velocities of that many atoms is simply not possible. In the year 2020, the global digital data storage capacity was approximately 10 zettabytes. A zettabyte is approximately 10 to the 21 bytes. So if you took all of the hard drives in the world, including the solid-state drives, and added their storage capacity or memory, you would get approximately 10 zettabytes of storage capacity. Now that's an enormous amount of memory, and yet it's not enough to record the positions of 10 to the 23 particles. So what we need is a more practical way of describing the state of a system. A more practical but incomplete description of an ideal gas would be to specify its large-scale parameters, those parameters or properties that are a little more tangible, so to speak, or can be more easily measured, like the volume, the pressure, the temperature, and the number of atoms in the ideal gas. This type of a description is referred to as a macrostate. So the prefix macro means large scale, while the prefix micro means small scale. A macrostate is a much more practical description of what a system is doing, but of course it leaves out a lot of detailed information, and in that sense it's incomplete. So what you're seeing here are essentially two extreme possibilities for the description of a system. The microstate is extremely detailed and microscopic. From a theoretical point of view, we wish we knew the microstate of a system, but from a practical point of view, what we often actually know or are capable of measuring is the macrostate of the system. It turns out the probability of a system doing something depends on its microstate, but what we have to learn to do is how to figure out that probability using a knowledge of its macrostate. On the next couple of slides, I'm going to show you some examples of how that can be done. Let's start with a simple example. Consider 3 gas molecules confined to a box of volume 2 cubic centimeters. A question that we might be interested in is the following. What is the probability, let's call it P1, that the gas occupies a volume of 2 cubic centimeters? In other words, we're interested in calculating the probability that the gas is distributed throughout the entire box. One way to answer a question like this is to consider all of the microscopic possibilities. So we have 3 gas molecules, and we're going to take our box and divide it into 2 halves. so that each section now has a volume of 1 cubic centimeters. And then systematically, we can consider all of the microscopic possibilities. You could have a situation where all three molecules are in the left half, or you could have the blue molecule in the right half, or the green one, or the red one. You can also have situations where there are two molecules in the right half and only one molecule in the left half. There are three of those situations. One final possible state is one in which all three molecules are in the right half. So each one of these pictures is essentially giving us a very microscopic description of what could happen. Roughly speaking, we can refer to each picture as a microstate. Notice here we're not really specifying the velocities of the particles simply because the probability that we want to calculate is not related to velocities, it's all about position. Now looking at these 8 possible microstates, we can see that 6 out of the 8, namely this one, this one, this one, and the 3 at the bottom, correspond to states where the gas occupies the entire box. In other words, there's at least one molecule in each half. So we can say that P1 is equal to 6/8. Another interesting question is the following. What is the probability, let's call it P2, that the gas occupies a volume of only 1 cubic centimeter? So now we're interested in situations where the entire gas is confined to only half of the box. Looking at our 8 microstates, we can see that 2 out of the 8, namely this one and this one, correspond to situations or states in which all of the gas is confined to half of the box. So we can say P2 is equal to 2/8. Now, admittedly, this is a very simple example. You might be asking what would happen if instead of 3 gas molecules, we had 1,000 or an Avogadro number of gas molecules. You might also be asking what would have happened if instead of dividing the box into 2 sections, we divided it into 4 sections or 1,000 sections. All of those questions can also be answered, but you would need a much greater knowledge of statistics and probability theory. So in this course, we'll limit ourselves to very simplistic examples like this one. Let's consider another simple example. Consider 3 gas molecules with a net or total energy of 3 joules. So we have a system that consists of only 3 molecules, and the total energy of the system is 3 joules. Of course, those 3 joules can be distributed in different ways among the 3 gas molecules. One question that we might be interested in answering is the following. What is the probability, let's call it P1, that one molecule possesses all of the energy? In other words, we want to calculate the probability that basically 2 of the molecules have 0 energy and 1 of the molecules has 3 joules of energy. To answer a question like this, we can once again start with a very systematic enumeration of all of the microscopic possibilities. So we can specify the energy of particle 1, energy of particle 2, and energy of particle 3. No matter how the 3 joules of energy is divided, the net energy should always add up to 3 joules. One possibility is that particle 3 has 3 joules of energy and the other 2 particles have 0 energy. Another possibility is that particle 3 has 2 joules of energy, particle 2 has 1 joule of energy, and particle 1 has no energy. In this way, you can systematically build a table that specifies every single microstate of this system. Notice here, we're not really specifying positions or velocities of the particles simply because the question is related to the energies of the particles and not their positions. In this respect, this example is different from the one on the previous slide. Once you've made a complete enumeration of all the possibilities, then you can answer the question by simply going through your table and noticing that in this microstate, in this microstate, and in this microstate, all of the energy belongs to only one particle. So in 3 out of the 10 possible cases, one particle possesses all of the energy, therefore P1 is equal to 3/10. We might also be interested in the following question. What is the probability, let's call it P2, that two molecules possess all the energy? So now we're interested in the probability that basically one of the molecules has zero energy. Since we have a complete enumeration of all of the microscopic possibilities, we can go through the table once again and note that in this case, in this one, this one, this one, and this one, at least one of the particles has zero energy. So now we can say that in 6 out of the 10 microstates, one of the particles has zero energy, or that two molecules possess all of the energy. Now again, this was a very simple example. You might be asking what would happen if instead of 3 gas molecules, we had an Avogadro number of gas molecules. You might also be wondering what would happen if each molecule could have fractional energy. So suppose a molecule could have, let's say, 1/10 of a joule of energy. Well, it turns out those questions can also be answered, but once again, we would need a lot more statistics and probability theory. So in this course, we'll limit ourselves to simple situations like this. So hopefully the last 2 examples showed that the number of microstates plays an important part in calculating the probability that a system has a given property. In other words, if you want to calculate the probability that a system has some property that you're interested in, you should start by systematically and methodically enumerating or listing all of the possible microstates. Once you have listed all of the microscopic states that are available to the system, preferably in the form of a list or a table, you can then go through that table and count the number of states that have the given property you're interested in. A little more precisely, let W denote the total number of microstates possible for the system. In this context, don't confuse W with work. We're using the same letter to denote a totally different concept. If W denotes the total number of microstates that are possible, then the probability of any one microstate, what we're denoting as P mic, is equal to 1 over W. So if the system has 10 possible microscopic states or configurations that it could be in, then P mic is 1 over 10 or 1/10. The probability of any one macrostate, what we're denoting as P mac, is proportional to 1 over W. By that I mean that P mac is equal to 1 over W times some number. To find that number, you first want to make a list of all of the possible microstates, then count all of the microstates that correspond to our macrostate of interest, and that's the number that we must multiply by 1 over W. So a macrostate here corresponds to a large-scale property that we're interested in, and what we have to do is look at all of the microstates that have that particular property. This is exactly what we did in our last 2 examples. In the first example, we found that the probability that the gas occupies half of the box is 2/8. We found the 2/8 by listing all of the possible scenarios or configurations or microscopic states of the system, and then we counted 2 of the 8 states as corresponding to the scenario we're interested in, namely that the gas occupies half of the box. That 2/8 can be expressed as 2 times 1/8. So 8 is the number of microstates, 1 over W, and 2 is the number of microstates that correspond to the property of interest. In the second example, we found that the probability that 2 molecules, any 2 molecules, possess all the energy is 6/10. We found that number by enumerating all of the possible microstates. So each line in this table corresponds to a specific microscopic description of the system. And then of these 10, we found 6 of them had the large-scale property that we're interested in, namely that two molecules have all the energy. We can express that probability as 6 times 1/10. The 10 is W, it's the number of possible microstates, and 6 is the number of microstates that have the property we're interested in. So you can see Pmac is proportional to 1/10, with the proportionality constant being 6 in this case. Now, calculating W, the number of microstates, is not always easy. In fact, usually it's quite a challenging task. But it should be obvious that the number of microstates depends on the number of particles. So the more particles you have in the system, the more possible microscopic states you have, simply because more particles means more ways to distribute those particles inside the volume of a box, or more ways to distribute energy among those particles. Very roughly speaking, W is equal to n factorial. So the exclamation symbol you see here is the factorial operator. N factorial simply means multiply n by n minus 1 by n minus 2 all the way down to 4, multiply by 3 by 2 by 1. So n factorial means multiply n by all the integers smaller than itself all the way down to 1. If you've ever solved problems having to do with permutations or combinations of objects, you've probably seen the factorial operator. Now, what I'm saying here is a very crude approximation, and I'm not going to prove it. You'll just have to believe me that the number of microstates is very roughly related to the number of particles factorial. For realistic systems, n is a large number. So in any realistic system, you might have 1,000 or 1,000,000 or an Avogadro number of particles. And so W, which is equal to n factorial, is a humongous number. It's a very, very large number. In fact, if you have your calculator with you, you can try this exercise on your own. 4 factorial, which is simply 4 times 3 times 2 times 1, is equal to 24. You can check that on your calculator or just do it by hand. 10 factorial takes a little bit longer to calculate, but you can do it on your calculator easily, and it turns out to be a big number, but a very manageable number. On the other hand, if you type in 100 factorial into most handheld calculators, you will get an error simply because this number is too big for most handheld calculators. It is a number that we can calculate. It turns out 100 factorial is approximately equal to 9.3 times 10 to the 157th power. So that's 93 with 156 zeros in front of it. Obviously an enormous number, and it's a number that most handheld calculators can't handle very easily. Now notice that this is only 100 factorial. If you have a system with 1,000 or 1,000,000 or an Avogadro number of particles in it, calculating the factorial becomes really quite difficult. For that reason, it is often easier to work with the logarithm of W. So since W itself is an enormous number, we often take the logarithm of that enormous number to get a number that is a little more manageable. For example, you can try this on your calculator also. 10 to the 100th power is something that is difficult to calculate on most calculators. If you try to compute 10 to the 100 plus 1 on your handheld calculator, you'll either get an error message or you'll simply get 10 to the 100 back in return, even though you added 1 to that number. On the other hand, almost every calculator can calculate the natural log of 10 to the 100. By property of the natural log of 10 to the 100 is simply equal to 100 times natural log of 10, and natural log of 10 is a very small manageable number, so the natural log of this enormous number just turns out to be 230.259 approximately. So the logarithm function is a type of function that has just the right properties for handling enormous numbers. It's a monotonically increasing function that can turn very large numbers into manageable numbers. This turns out to be a very useful property when we start discussing entropy. So at last, we're in a position to define entropy. For an isolated system, entropy is defined by this equation. We're using the letter S to denote entropy. As I've said, W refers to the number of microstates or microscopic states that the system can be in. Since W is a very large number, we choose to discuss the natural log of W. And Kb, of course, is a constant you've already seen. It's known as the Boltzmann constant. In fact, this equation was first discovered by Ludwig Boltzmann circa 1890. If you happen to be in Vienna, Austria, and you happen to visit the Central Cemetery there, you will find Ludwig Boltzmann's grave there, and this equation is etched at the very top of his gravestone. Recall that the Boltzmann constant has units of joules per Kelvin, and W is unitless. It's a number of states, and so the SI unit of entropy is basically joules per Kelvin. One could define entropy without multiplying it by Kb. However, it turns out the units joules and Kelvin are very convenient for thermodynamic applications, so traditionally entropy has been defined by taking the natural log of the number of states and then multiplying it by a convenient constant. A system with a large entropy basically has many microstates available to it. So you should think of S in the same way, roughly, that you think of W. S is essentially an accounting of the number of microscopic possibilities that are available to a given system. When a system has a very large entropy, people sometimes describe it by saying that it is difficult to guess the state of the system because there are so many possibilities, or that the system is complex or chaotic or even random. These are not very precisely defined words. It's best to think of entropy as describing the number of possible microstates that a system could be in, but very roughly speaking, you can think of entropy as a measure of chaos or randomness or the complexity of a system. Alternatively, you can think of entropy as the thing that tells us how probable an individual microstate is. Recall that we decided P mic is equal to 1 over W. If you come to this entropy equation at the top and solve for W, you'll see that W is equal to the Euler number raised to the power S over Kb. Recall that the exponent is the inverse of the natural log. If you take this expression for W and plug it down here, since we're interested in 1 over W, we find that P mic is equal to E raised to the power minus S over Kb. So an alternative interpretation of entropy is as the thing that determines the probability of individual microstates. Now that we have a basic understanding of entropy, we can return to the second law of thermodynamics. Recall that there are three equivalent versions or forms of the second law of thermodynamics. In the last lecture, I introduced you to the Kelvin-Planck version and the Clausius version. The entropy version of the second law states that for any isolated system, the change in entropy must be greater than or equal to 0. This statement is sometimes interpreted as saying that a system tends to maximize its entropy. Now that we understand that entropy is essentially an accounting of the number of microstates available to a system, we can better understand why entropy should always increase. Entropy is maximized because the system seeks the most likely macrostate. Remember that a macrostate is a description of the large-scale properties of a system like pressure and temperature. The most likely macrostate is the state that corresponds to the largest number of microstates. We can say this a little more mathematically by returning to Boltzmann's definition of entropy. According to Boltzmann, Entropy S is equal to the Boltzmann constant times the natural log of the number of microstates. We can differentiate entropy with respect to W, and we find that ds dW is equal to the Boltzmann constant times the derivative of the natural log of W, which is just 1 over W. By rearranging this equation, we find that an infinitesimal change in entropy is equal to Kb over W times dW. So a change in entropy corresponds to a change in the number of microstates. When we say that the entropy of a system must increase, we're basically saying that the number of microstates must increase. In other words, the system is more likely to find itself in a macrostate with an increasing number of microstates. Ultimately, the three versions of the second law of thermodynamics are all equivalent to one another. Ultimately, the reason that the efficiency of a heat engine is less than 1, or the coefficient of performance of a heat pump is less than infinity, is because for realistic systems, delta S is greater than 0. For realistic systems, the system is always moving towards a macrostate that encompasses a greater number of microstates. This last statement is not obvious, but it is nonetheless true. In our next lecture, we'll turn to doing some practical entropy calculations for some familiar systems. And that is the end of this lecture. Thank you for your attention.